10 challenging IR spectrum questions. At the end of the video, you will walk through ideas probably never seen before, and try to answer each question on your own before I explain the answer. Here we have 5 molecules, 4 alkynes and 1 cyanide, and above there is an IR spectrum of one of these molecules. So let's analyze the spectrum. We could look for the sharp bands of alkyne and cyanide at the triple bond region, and it really does exist. So we could eliminate choice A because it has symmetric alkyne, so its dipole moment is equal to 0, so its band should not exist. Now, is it the choice B, the asymmetric alkyne? If so, there must be a band for the sp carbon-hydrogen stretch in the hydrogen region at 3300, but nothing there, so choice B is also out. Now it should be one of the rest, but note that there is an extra band in the triple bond region, which corresponds to answer choice D. It has 2 alkyne groups in a different environment, so you will have 2 alkyne bands, and it really does exist in the spectrum. Let's look for this one. We have 3 molecules that have carbon-carbon double bond, and have a try with it on your own for a second. The answer is simply choice B, where there is no sp2 carbon-hydrogen stretch in the hydrogen region. Now let's work on our third question. Which of the following molecules correspond to this IR spectrum? The first thing we can easily identify is the presence of a carbon-carbon double bond band. So we could eliminate choice A because it's a trans isomer, so the dipole moment is nearly equal to 0, so no band will occur for it. For the choice B and C, how to differentiate between them? There are 2 ways. The first way is the position of carbon-carbon double bond band, where the conjugated alkene will have a lower wave number compared to that of unconjugated alkene. Remember that the unconjugated alkene ranges from 1600 to 1680, and here in the spectrum is located at 1640, so it's the choice C. The other way is the intensity of the band. For C, it should be weaker than that of B, because in C there is only 1 carbon-carbon double bond, while B has 3. And also, C is a nearly symmetric alkene. But some will say, isn't it symmetric alkene? Actually, its true form is not this form. Its true form is the chair configuration you could be familiar with in stereochemistry. Now let's move on to spectrum number 4. Looking out to the choices, we have 1 carboxylic acid group, 1 alcohol, and 2 phenols. Well, we have a broad band, not a massive band, so we could eliminate choice A. So is it benzyl alcohol or phenol? Well, we could check the carbon-oxygen stretch, where it's higher with phenols. With phenols, it's at 1200 due to the higher double bond character, and it really does locate at 1200. So choice B is out. So is it also or bara substituted phenol? It could be your first time to know that we can distinguish them using IR spectrum, but it's really not that complicated. Simply draw a line at 800. If there is a strong band before 800, so it's also substituted. If after 800, so it's bara substituted. Exactly like this one. So it is the choice C. Let's look for the fifth question, where we have 4 amine molecules. First, do we have a benzene ring or not? Well, we have a pair of carbon-carbon double bonds bands at 1600 and 1450, and also aromatic overtones, so we do have a benzene ring. So choice B is out. Now is it a primary amine or secondary amine? We only have one NH stretch band, So definitely we have a secondary amine. So choice A is also out. Now which one is the answer? C or D? Where both are secondary amine and have a benzene ring. But there is a difference. C is not aromatic amine and this effect on the intensity of the band, where the aromatic amine has a higher NH stretch band intensity than that of aliphatic amine. And we do have an intense band, so the answer is D. But for your information, this is the shape of the aliphatic secondary amine. You will notice that the intensity of the band is lower than that of the aromatic amine. Next, let's take a look at question number 6. Look at this massive band. It's pretty clear that we have a carboxylic acid group, but is it C or D? Well, there is a band at 3100 which corresponds to the sp2 hybridized carbon hydrogen stretch overlapping with the oxygen hydrogen band, which makes the answer is C. Next, let's take a look at question number 7. We have four molecules have an aldehyde group, but which does correspond to this IR spectrum? Well, choice A has a cyano group, but there are no sharp bands in the triple bond region, ruling out choice A. But look at this broad band, which corresponds to the oxygen hydrogen band, ruling out choice B. Now, C and D, which is the answer? Simply, we need to remember that the hydrogen bonding weakens the carbonyl bond, which lowers its wave number. And this will be present in the ortho substituted because it's near from the carbonyl group. Not like the para substituted, it's far away from the carbonyl group, so it will not weaken its bond. So we will check the carbonyl band. Is it much lower than usual or not? Here our carbonyl band is located at 1680, which is way lower than usual, so the answer is D. Now let's move on to spectrum number 8. Looking out to the choices, we have three ester molecules. But note that we have an sp2 hybridized carbon hydrogen stretch at 3100, so we could eliminate the choice A. So which one of these is the correct answer? The difference between them is the position of the carbonyl group. One beside the ring, so it's conjugated, and the other is the oxygen beside the ring. And we know that the conjugation decreases the double bond character and therefore the wave number. But look here, it's way greater than normal. The unconjugated ester carbonyl band is located at 1735, but here much higher. So we are left with choice B, but why the wave number is high? This is because the lone pair on oxygen starts the resonance and leave a positively charged oxygen which needs to be stabilized, so it withdraws the electrons from the carbonyl, which increases the double bond character and therefore the wave number. To the interesting question number 9. Try to guess the answer as you can. Well, there is a clear carbonyl band here, but note that it's splitted into doublet bands. It's not acid anhydride, where the acid anhydride has clear, intense two separate bands. But here, both are nearly in one band. So it's diketone. So it could be A, B, or C. But in B, there is a benzene ring, and there is sp2 hybridized carbon hydrogen stretch, so the answer is B. To the last question. Well, it's quite strange in the carbony region with this mess and small OH band that looks weird. What the heck is this? The only way this is explained is through the presence of tautomerization between ketoenol forms. The enol form is the reason behind the presence of a small OH band, and these three carbonyl bands corresponds to the asymmetric and symmetric keto forms, and the carbonyl which located at a lower wave number is the one in the enol form, because the hydrogen bonding decreases the wave number, so this corresponds to the enol form. And that's for today. And tell me in the comments how many questions you answered correctly. And if you liked the video, hit the like and subscribe to the channel. And thank you for watching. And see you soon.